Drones have always been a subject of great fascination, which not only tantalized both sides of the Iron Curtain, but invaded the minds of some of the world's earliest aviators. This video will attempt to provide a somewhat comprehensive look at the history of Soviet pursuits in the development of this technology, from the early Cold War to its end. I will provide brief summaries of notable proposals and developments, but the focus of this video is primarily those that entered service, all of which were focused on reconnaissance.
Its value can be measured literally in the number of lives and the firepower saved for each target killed.
I should note that the equipment displayed in this video paved the way for the success of modern unmanned aerial vehicles. So I hope this video provides some information to those who may not have been acquainted with it as to where drones came from, specifically on the Soviet side of things, and their significance. I hope you enjoy. Before I start this video, I need to apologize. I am not home right now, and so my microphone is abysmal. You're going to have to cope with it for this one video. Please forgive me. The development of drones within the USSR began with the desire to construct supersonic intercontinental cruise missiles. Initially, this subject was pursued by OKB-1 or Ni-88 under the leadership of SP Korolev. By decree of the Council of Ministers on February 13, 1953, the development of a two-stage cruise missile with a range of 8,000 kilometers was approved. OKB-1 was chosen to design, manufacture, and refine this hypothetical weapon system. To reduce the time and cost required to undertake such an endeavor, the R-11 short-range ballistic missile was chosen as the weapon's first stage, which meant that only a unique second stage would be developed. Ni-88 would assume the development of a control system employing celestial navigation to guide the missile. In January of that year, preparations were made to produce the experimental missile. 10 flights to test the navigation system through a flying laboratory were conducted. After further refinement, it was decided that abandoning the project was a reasonable conclusion, and that more design bureaus would be required to produce such a complex. Because OKB-1 was already working on the R5 and R7, upon receiving the order to develop the previously described weapon, it was decided on May 20th of 1954 that the development of long-range cruise missiles would be handed off to OKB-301, headed by S.A. Lavochkin, and OKB-23, headed by V.M. Yastreb. Two new intercontinental missile programs were outlined in Decree No. 957-409, with the expectation that they would be able to strike targets in the United States. These two new targets fell under the designation KRMD, or Cruise Missile with Intercontinental Range. The KRMD program resulted in the creation of the Buria, or LA-350, created by OKB-301, and Buran, created by OKB-23. LA-350's Celestial Navigation Complex was designed by OKB-165, which allowed the missile to dive onto a target once it got within 25 kilometers. After extensive analysis, this concept was refined in 1955, after which manufacturing of its boosters began at Plant No. 207. Flight tests were conducted on July 31st of 1957 at GCP-4. The first launch transpired on September 1st of 1957. Here, the team's optimism was somewhat reduced when the missile failed and exploded on the ground after falling a short distance. The second launch was similarly unsuccessful, with a premature detonation occurring after just 31 seconds of flight. The third flight was slightly better, with 63 seconds being sustained, and on the fourth, 81. It was only on May 22nd, 1958, during the missile's fifth test flight, that separation occurred and the missile demonstrated its ability to cruise. This was followed by 3 more failures. On December 28th of 1958, 309 seconds of powered flight occurred. Finally, on the 12th flight, the navigation system was tested on the missile, but it too was unsuccessful. Modernized boosters were affixed for the 13th test flight, which featured a shortened combustion chamber. This allowed for 10 minutes of flight to be engaged. On December 2nd, 1959, LA-350 managed to fly 4,000 kilometers, and during its final launch, which took place a year later on December 16th, 6,500, before the missile dived onto the target. 19 of these systems were manufactured and 18 launches were carried out. Work on the LA-350 was terminated on February 5th of 1960 as the R-7 demonstrated far greater capabilities and was actually working as intended. But this was not the end for the LA-350, as the same decree that cancelled its development as a cruise missile, that being number 138-140, also proposed its modification into a reconnaissance drone that could conduct high-speed, high-altitude photography of strategic assets. The decree also noted that existing missiles were to be turned into training targets for the S-200. The last 5 Burias went through a short rebuild period, after which 4 launches were conducted to confirm the feasibility of deploying LA-350 as a long-range reconnaissance drone, which ended with unfavorable results. The final LA-350 was fired on December 16th of 1960. Beginning in 1956, OKB-240, headed by S.V. Ilyushin, prospected the creation of a UAV capable of striking targets after conducting limited reconnaissance. This project was abandoned as the technology did not exist and funding had not yet been secured. All we know about this project was that it was to employ the VK-15B turbojet engine. Around this time, OKB-156, headed by A.N. Tupolev, was issued a proposal to produce a 3-stage liquid propellant rocket with a mass of 240 tons. Its requirements stated that the rocket had to be capable of reaching an altitude of up to 50 kilometers and accelerate to a speed of Mach 17, which is a bit optimistic to say the least. Eventually, it was concluded that the system, if produced, would be capable of reaching a distance of 12,000 kilometers, with a circular error probable of around 10 kilometers. Work on this weapon was approved on March 19th of 1957. OKB-156 was tasked with studying this prospective missile, designated Project KR, and later Project DP. OKB-156's work made it possible to develop a preliminary design by the end of 1958. Here it earned the title of Unmanned Strike Aircraft 123. The application of the NK-6 engine reduced its range to 9,500 kilometers, but the circular error probable of 10 kilometers remained. It would fly at altitudes of 22 to 25 kilometers at a more achievable speed of 2,700 kilometers per hour. Simultaneously, in 1956, a recently created team within OKB-156 began work on a medium-range missile to complement the 123, designated Unmanned Strike Aircraft 121. This system offered a range of 4,000 kilometers, which was almost half the 123's range. Its development was approved on the 23rd of September 1957. Expectations were set, that it would be tested no later than mid-1959. The Tu-121, as it was designated, employed KR-15-300 engines developed by OKB-300. Solid propellant launch boosters, called PRD-52, with a thrust between 75,000 to 8,000 kilograms, were used to carry the missile to a height of 100 meters at a speed of 170 kilometers per hour. The KR-15-300 cruising engine had a rather short life of only 15 hours, and could provide 15 tons of thrust for 3 hours with the afterburner engaged. The Tu-121's cruising altitude was 20 kilometers, which allowed it to reach a distance of 300 kilometers. After transitioning to a 50-degree dive to the target, its warhead was set to detonate 2 meters above the ground. The missile was launched at an angle of 12 to 15 degrees from a modified Yaz-214D produced at the Yaroslav automobile plant from 1951 to 1959. It was designed by A.V. Nadeshkovich and designated ST-10. The launcher was additionally equipped with a crane. During transport, Tu-121's wings, control surfaces, and booster were stored separately. They were then assembled on site. ST-10 also served as storage for these components. A special vehicle separate from ST-10 transported Tu-121's warhead and guidance equipment. A generator was included on board the transportation vehicle to start the KR-15-300. Initially, rails almost 20 meters long were chosen for the launch installation. Later, a young engineer named V.I. Blizinuk, who would later become the OKB's chief designer, suggested 10-meter-long rails be introduced. Further testing and operation of the installation confirmed this was indeed the right decision. In the second half of 1958, the first mock-up Tu-121 was ready. In the winter of 1958 to 1959, firing tests began at the Fastavo range near Moscow. These tests confirmed the effectiveness of the boosters. By the summer of 1959, the first operational Tu-121 was transferred to a base located in Vladimirovka. Preparation for flight testing began. Adjustments were conducted until the end of August, and finally on August 25, 1959, the first Tu-121, at 6 o'clock in the morning, to the sound of the USSR national anthem, which played from a loudspeaker located nearby, took to the skies. Tupolev himself was present at the first launch. This flight was successful. It was followed by several more successful launches. In total, 5 were fired, and preparation for serial production was already being discussed. During the first launches, the safety of launching the system with the transport vehicle's operator still inside the cabin was tested. This was done using a rabbit that some sources claim was captured on site and was then placed in the cabin. It survived, and so launches from the cabin were adopted as standard practice for all subsequent drones developed by Tupolev. However, this success was limited as in 1960 all work on the Tu-121 was cancelled. While Tu-121 was being tested, Tu-131 was proposed, which was very similar, its primary difference being increased fuel capacity, which allowed for a near intercontinental range of 6,000 kilometers. Some sources state that Yaz-214D was actually not chosen as the transport platform for the Tu-121, but instead the Maz-535. As these cruise missiles were in development, Tupolev was hard at work proposing completely absurd ideas like the Tu-100, which would feature a manned and unmanned variant. These aircraft would be released from a carrier platform, most certainly a strategic bomber, at around 1,000 kilometers from the target. They would then fly at a speed of 1,500 kilometers per hour, deliver a nuclear strike, before returning to an airfield 500 kilometers from the target. This did not satisfy, and so an operational range of 6,500 kilometers was proposed. Interestingly, this futuristic concept was already being designed in 1954. This premature variant was to employ swept wings and 2 AM-11M afterburning engines. In 1955, the power plant was modified to D-20 turbofan engines with a maximum thrust of 6,000 kilograms. The reduced fuel consumption of the D-20 engines made it possible to expect an increased range with the possibility of raising speed to 1,800 kilometers per hour. A new aircraft, the Tu-96, was proposed to carry the Tu-100, one of which was built in 1956. While the Tu-100 was never produced and only remained a concept, Tupolev kept developing aircraft to carry it, such as the supersonic intercontinental bomber Tu-128 and Tu-129. Finally, it was cancelled in 1958. Here I will quickly cover the brief history of unmanned interceptor programs, which were a strange obsession between 1940 and 1970. Immediately after World War II, from 1954 to 1947, plans to create an unmanned radio-controlled interceptor were laid out. 30 of these experimental interceptors were to be produced, but this project never panned out. Following this concept, periodic attempts would be conducted to realize the idea of an unmanned aircraft for striking targets on the ground and engaging threats in the air. Order number 366 of the State Committee for Shipbuilding, dated 16th of November 1959, proposed an unmanned aircraft that would carry anti-ship missiles, an unmanned interceptor to defend friendly vessels, and an unmanned reconnaissance aircraft. This project was never assigned to an OKB and therefore was not considered past a first requirement draft. The idea was reconsidered in 1970, but once again failed to get off the ground. This unmanned missile carrier would have been capable of flying 300 kilometers and would have employed its munitions 150 kilometers from the target. They would have flown at an altitude of 3 kilometers at speeds exceeding Mach 3 to 4. These drones would be flown by pilots aboard bombers, shadowing them. The unmanned interceptor requirements were centered around the need to destroy both low and high altitude targets. The drone itself was not expected to survive, but its ability to return after a mission was considered important, as its expensive guidance equipment would need to be recovered. These unmanned interceptors were interestingly considered cheaper than developing a long-range surface-to-air missile. They would feature a takeoff weight of 15,000 kilograms and an operational radius of 500 kilometers. The interceptor was also to have a maximum flight speed of Mach 2 to 2.5 and a ceiling of 25,000 to 30,000 meters. V.N. Pchela, a somewhat notorious individual, also considered the idea of an unmanned interceptor for use in the Soviet Navy independent of these proposals. His idea differed somewhat. These drones were to be capable of destroying vessels with their guided munitions, but would also possess the additional capability of ramming ships and aircraft once they expended their weapons. This was especially absurd considering the original program was so that they could recover the drone and operate them as a cheaper alternative to surface-to-air missiles. I don't really know what he was thinking when he proposed this. In the early 1970s, serious work began on an unmanned fighter known as Berkut. While this program did not go anywhere, it was later proposed that MiG-21s removed from service should be modified into cruise missiles for striking targets on the ground. This was seriously considered, but quickly became costly and difficult to implement. According to evaluations, converting even a small number of obsolete aircraft would have required the creation of new units equipped with control systems for what were essentially single-use UAVs, as well as the corresponding training facilities, equipment maintenance, and so forth. It also proved impressively expensive to make these conversions, especially considering the fact it would have required additional production of expensive onboard equipment designed not only for guidance but also for target detection. Following the 1950s, due to the constant development of cruise missiles and target drones, the technology finally existed to make practical, accurate reconnaissance drones. Previously, limited success was achieved when it came to equipment stabilization, the activation of reconnaissance equipment ensuring photos were taken of the target, and the ability for these systems to land after every use. In the 1960s, everything changed, as all of these capabilities seemed to mature simultaneously except one which I will explain later. The first successful reconnaissance drones developed in the USSR were out of a need to study the effects of experimental nuclear weapons, specifically radiation levels right after detonation. In 1949, 5 Yak-9Bs were modified into radio-controlled unmanned dosimetric monitoring aircraft. I'm not saying dosimetric in this video, you can't yell at me in the comments. For taking samples of particulates thrown into the air by the explosion, these drones were equipped with barrels that featured a special mesh filter. These aircraft were controlled from a Tu-2 that acted as an airborne command post. 10 Tu-2s were converted for this purpose. Taxiing and takeoff was performed without a pilot. After a myriad of tests and modifications, these aircraft were transported by rail to Semipalatinsk. During preparations prior to the system's actual employment during a nuclear weapons test, 2 aircraft were lost. There are many conflicting stories given in various publications about the application of these drones. Milishenkovsky and Rebrov state on the 29th of August 1949 one of these Yak-9s flew through a mushroom cloud. Yet in the memoirs of Kulikov it is stated that these aircraft did not arrive until 1951. Either way, we do in fact know that difficulties arose during landing. As a result, shortcomings were identified in the ability for the USSR to develop advanced control systems for unmanned aircraft. One of the first dedicated reconnaissance drones produced in the USSR was a modified Yak-25, designated Yak-25RV-2. The manned Yak-25RV-1 differed from the earlier Yak-25R through the reconfiguration of its fuselage, replacement of the sweep wing with a straight wing, and a change in the landing gear retraction scheme. The unmanned model performed the same missions as the manned counterpart, namely photographic reconnaissance and radiation reconnaissance. The aircraft would fly to the target automatically, only following preset instructions provided before it was launched. Serial production of this model was carried out at Plant No. 99 in Ulan-Ude, where 81 were produced. Once the manned variant became obsolete, the 71 Yak-25RV-1s produced in No. 99 were converted to radio-controlled target drones. Sources are unfortunately conflicted on if Yak-25RV-2 was only ever a target drone or if it did feature proper reconnaissance capabilities, but considering how well it is documented in some sources, I do believe that it was at some point a reconnaissance system. In the early 1960s, at Central Scientific Research Institute No. 45, in accordance with Order No. 366 of the State Committee for Shipbuilding dated November 16, 1959, technical requirements were developed for a specialized unmanned reconnaissance aircraft known as the Follow-On Reconnaissance Vehicle. This drone was created for single use alongside submarines for reconnoitering naval formations. It was envisioned that by 1965 a drone would be created analogous to P-20 and P-22 that would be capable of selecting formations, determining their composition and coordinates, after which all of this data would be transmitted to the carrier submarine 1,500 kilometers away. This was pretty optimistic for the time. Issues quickly arose when it came to transferring data, which was only made worse by the fact that OKB-240 stopped producing the P-20 and P-22 altogether, which meant that the unmanned reconnaissance vehicle could not be developed. I must note that, uniquely, the problem with this project was not actually the ability to control the drone, which demonstrated how far these subsystems had come in such a short period. The 1960s were important not just from a technological standpoint, but also from a theoretical perspective. It was becoming clear that UAVs made it possible to collect a wide range of intelligence and deliver it to processing and decryption stations for subsequent analysis, and use in an exceedingly short period of time. Much faster than that of manned aircraft. In addition, UAVs with high speeds and flight altitudes were less vulnerable to air defense systems, which made their use far more preferable to manned aircraft, which put the pilot and expensive airframe at risk. The first prototype reconnaissance drone, which sought to meet these demands, was to be built off the back of the development already engaged to realize the Tsibin RSR. You'll notice a trend of over-optimism in many of the characteristics in these programs, and that is carried on here. The original manned variant, known as R-020, was to be launched from a Tu-95K at a distance of 4,000 kilometers from the base it would return to. It would fly at 3,000 kilometers per hour and would land on its own after completing a successful reconnaissance flight. Later proposals under the RSR program would feature the ability to take off without the assistance of a Tu-95, but by then OKB-256 was incorporated into OKB-23, and in the end of 1960 it was dissolved entirely and its projects terminated. Despite this minor setback, Tupolev would step in and finally, after years of trial and error, solve the unmanned reconnaissance platform problem, introducing the first practical drone employed by the Soviet Army. The subdivision that would realize this project was by no means a small organization. Following its creation, it was jokingly referenced as an OKB inside the OKB, as it mimicked the exact structure of Tupolev at large. It was staffed by younger, enthusiastic engineers with the intention of bringing new ideas into the picture. They were assisted by experienced veterans who had spent much of their careers at the OKB. Together, they received the designation Department K. As the Tu-121 was cancelled, the longer-range 123 soon followed, resulting in all of the work conducted by Department K being discarded just as quickly as these systems began to literally get off the ground. Luckily, it would not go to waste, as later that year, on August 16, 1960, a decree of the Council of Ministers of the USSR on the creation of a long-range unmanned reconnaissance system was issued, which received the designation DBR-1 Yastreb. The DBR-1 would reuse much of the technology developed for the Tu-121, but this did not mean that Department K would have an easy time developing such an ambitious aircraft. Firstly, a new long-range, high-powered camera was required to facilitate accurate photography at altitude. This by itself was not terribly difficult, but ensuring such a sensitive device would not be affected by heat or vibrations during flight was problematic. New guidance equipment was also needed to ensure the aircraft could operate without receiving any commands from the ground. Though the most difficult part of the program would be landing what was effectively a cruise missile with a camera on it, as its photographs and expensive components had to be recovered. Additionally, documentation was required to prepare units for receiving what was in many regards a radically new system with a very unique use case. The expected application of the DBR-1 was reconnaissance of strategic and operational assets, such as nuclear deliverance platforms, airfields, industrial facilities, naval bases, ports, large troop concentrations, air defense weapons, and confirming the effectiveness of nuclear as well as chemical weapon deployment. The aircraft could detect radio signals emitted along its flight path and record them for analysis on the ground. These signals made it possible to determine the type of communication equipment and where it was located. DBR-1 was broken into 6 sections, with all of the reconnaissance equipment being located in the first. This compartment was designated F1 and weighed 2,800 kilograms. This was the only section that needed to be recovered, and featured a parachute to ensure its safe descent. F1 was also fitted with a cushion that would deploy before it hit the ground to ensure that all of the sensitive components were not damaged by the impact. Present within this compartment was the oblique photography camera known as AFA 41-20M, and 3 planimetric cameras designated AFA 54-100M. The AFA 41 series of cameras were used across a wide range of reconnaissance aircraft and were intended for photography at a range of 20 kilometers. The camera provides an exposure range from 1/70th of a second to 1/700th of a second. The shutter is released by the discharge of a spiral spring actuated by a special solenoid. The exposure duration is set remotely. The shutter is cocked by an electric motor. Film is transported by a motor which moves the take-up reel through a reduction gear. The command and control device, as it was labeled, allowed the operating mode of the camera to be set within an interval from 3 to 90 seconds, with a cycle of 2.25 seconds, and also allows for remote adjustment of exposure time. The camera includes an RB-TDA radio altimeter and a gyro stabilization system. The AFA-54 has 2 variants, one with a focal length of 75 centimeters and another with a focal length of 100 centimeters. The variant employed by DBR-1 is the latter. Unlike the AFA-41, this camera is semi-automatic and is set remotely to function at a specific distance from the target. These cameras are provided in sets, 2 of which exist. The DBR-1 most likely makes use of the 3-direction set. Here, the cameras are paired with an automatically rotating camera integrated into an AK-AFU 33M container. Though it should be noted, no source actually specifies which set the DBR-1 employs. Both cameras are paired with a light measuring device to automatically set the exposure time, alongside an SRS-60 radio reconnaissance device and Doppler navigation station. These components were protected with heat-resistant glass and a precision airflow system to prevent optical distortion. Further redundancy was introduced through an air conditioning and overpressure system to ensure the cameras were not disturbed during high-speed flight. The compartment housing all of these components was to be removed and serviced regularly inside a trailer known as Card 1NP, which was towed by a ZIL-157, and was configured to maintain the climate required by the camera to function properly. These trailers were then converted into command posts after launch to monitor the aircraft's flight path. As they were equipped with 2 powerful electric heaters, they were frequently employed as shelter during winter exercises. The F1 compartment was affixed to the DBR prior to launch using a crane. DBR-1 featured a total fuel capacity of 19,000 liters, Its KR-15-300 engine had a static afterburning thrust of 15,000 kilograms and a continuous afterburning thrust of 10,000 kilograms, which it maintained through the duration of its mission. 2 solid-fuel rocket boosters known as PRD-52, each producing 75 to 80,000 kilograms of thrust, were used for takeoff and acceleration. The boosters were jettisoned 5 seconds after liftoff. For better engine performance at lower speeds, a subsonic diffuser was affixed to the air intake. The diffuser fit tightly to the air intake fairing, which served to smooth airflow during the first 9 seconds of flight. It then separated from the aircraft. DBR-1's wings were stored separately from the aircraft and attached before flight. These wings had a sweep angle of 61 degrees at the leading edge and a reflex sweep angle of 3 degrees and 55 minutes. The aircraft's tail assembly comprised 3 control surfaces set 120 degrees apart. Unlike the wings, these were mechanical and could move to ensure stability. This arrangement was optimal for high-altitude supersonic flight. The drone was supported by the launch tractor truck designated SARD-1 STA-30, towed by the MAZ-537 missile tractor, and the control start vehicle CARD-1S, also called KSM-123, which contained diagnostic equipment. The command to launch was issued from the STA-30's cabin. This could also be done from a remote control panel separate from the vehicle. This was in many regards the preferred launch option. The aircraft launched at an angle of 12 degrees. At the moment of launch, the aircraft experienced 4 to 8 Gs. After completing the pre-programmed flight, and turning to begin the return flight, at a distance of 400 to 500 kilometers, the onboard guidance equipment was automatically engaged. The aircraft was then detected and identified on an accompanying radar. After identification, radio commands were issued to ensure the aircraft delivered its equipment to the right spot. The pre-programmed instructions issued a command to stop the engine, to drain the remaining fuel from the tanks, and to change the aircraft's flight trajectory to a climb in order to reduce speed. Then a command was issued to deploy the braking parachute. After that, the nose section was unlocked and separated from the rest of the aircraft. The rest of the drone was significantly cheaper, so it was acceptable for it to be destroyed on impact. We're going to come back to that point later. After instruments landed, its radio beacon began to operate automatically, which made locating it far easier. At the conclusion of the operation, the reconnaissance data was removed from the recoverable compartment and delivered for decryption. State trials with the Ministry of Defense took place from September 1961 to December 1963, after which the drone entered service under the designation Tu-123. It officially entered service with the Air Force by decree of the Council of Ministers of the USSR No. 444-178, dated May 23, 1964. Serial production of the aircraft was carried out at the Voronezh Aircraft Plant, No. 64, and continued from 1964 to 1972. Only 52 were constructed. The Tu-123 remained in service until 1979. In the early 80s, the last Tu-123s were officially removed from service. We don't know exactly when this happened. The primary units present in a Tu-123 squadron were 2 launch detachments who conducted pre-flight maintenance and, as their name suggests, deployed the drone. The Engineering Technical Service, who maintained the drone year-round and prepared for transfer to the launch squadron, were broken into 4 groups, who took care of the engine, guidance equipment, cameras, and transportation separately. The group that maintained the guidance equipment and radio-electronic components were accompanied by warrant, technicians, and senior technician specialists. This was mirrored in the transportation group. The squadron's search and recovery group were tasked with locating the Tu-123's nose after it had separated from the drone. TZ-22 fuel tankers and other logistical assets were included alongside a medical department. Each squadron operated a minimum of 12 Tu-123s. A laboratory was attached for processing the photographs and data obtained by the aircraft after the F-1 compartment had been recovered. These units moved at night, in peacetime, so that they could camouflage the position that they were redeploying to. To staff these units, front cruise missile formations were reorganized in the early 1960s. 4 of these units were converted, 1 from the GSFG and 3 in the USSR. The first squadron was formed in Latvia. Alongside this drone squadron, special units were created to fire off its remaining cruise missiles that were no longer required by the unit. The missiles were moved to a range in Ostroluk, where they served as low-flying targets for fighter training. From 1961 to 1968, about 230 missiles were launched. Only a few were lost due to malfunctions. This continued the trend of Soviet cruise missiles becoming drones. Anti-cruise missile training conducted by fighter aircraft was a common practice across the Warsaw Pact. For example, in Poland, MiG-23MF pilots referenced this as intercepting the bomb. The second to be formed, known as the 10th Separate Squadron, was located in western Ukraine. The third squadron, known as the 4th Separate Guards Squadron, was created from a disbanded unit hailing from the GSFG around this time as well. Interestingly, it was the smallest formation of the four and operated with a reduced staff. This was most likely due to the fact that the squadrons located in the USSR possessed the ability to penetrate German airspace from a point of relative safety. These early squadrons had a lot of issues, notably weak logistics, long convoys when on the march, long data delivery, and worst of all, the inability to recover the entire aircraft. Many units within the USSR jokingly referred to drone squadrons as play regiments, as they only conducted launches once a year, and the complete lack of launches from 1976 to 1977 did not help this reputation. This was not the fault of these formations, though. It was instead a result of how cumbersome the Tu-123 was to operate. Preparation for training endeavors required a great deal of time and involved a large number of special and general-purpose vehicles. The workload during these mock operations was grueling, as the unit had to prepare these systems in an exceedingly short period of time, after which they barely had time to rest as they had to march to the launch zone and conduct the exercise. Engineers within these formations jokingly referenced themselves as pilots, as they did everything to ensure the aircraft could fly. Flights usually lasted 9 minutes and were tracked by the accompanying radar and judged by observers located 1 kilometer away. In 1977, operations involving each drone squadron were planned, and much of the year was spent getting ready, stocking up on insect repellent and so on. In early June, these units conducted a 10,000-kilometer march to the Far East. The vehicles belonging to the unit had their registration plates removed to camouflage them from onlookers. The unit's personnel were also instructed to wear civilian attire. Only the advance guard of the unit carried weapons and wore their uniforms. After 15 days, the unit arrived, unloaded their equipment, and began preparing. The conditions were severe, and tents did not shield the soldiers from the environmental conditions of this region. Each squadron prepared 2 drones and conducted sequential launches. The 10th Squadron's drone malfunctioned and was lost in the Amur floodplain. The operation was suspended, and investigations began as to why this transpired. Local residents were interviewed who stated they observed a missile fly over their homes, likely originating from the Chinese border, that struck the drone, downing it. This was not confirmed due to the state of the wreckage being impossible to parse, and so the training was resumed. This was difficult as the Latvian squadron was struggling to launch their drone due to a failure with the intake. As a result, the flight was cancelled. The final flight was performed by the 4th Squadron. Because no pit could be dug to shield the launch detachment's commander, he was provided with a tank for the remainder of the exercise, from which he could safely launch the drone from inside of. The launch transpired as normal, but when the drone attempted to make its return trip, the detachment instructed to guide the aircraft via radio controls from Komsomolsk-on-Amur made an error and took control too early. This resulted in a landing that, while successful, placed the capsule in a position where it could not be recovered by helicopter. An expedition was launched to recover the equipment. After hiking to the site, the capsule was inspected. The success of the operation was verified, and all sensitive equipment was destroyed. This was the last flight ever conducted by a Tu-123. Tu-123 had an interesting service history. It was considered an unreliable, difficult to maintain, and deeply cumbersome system. Its bulky cables, inaccessible engine, and small production batches infuriated the squads equipped with it. The unit's cranes and cargo vehicles often went on what were described as vacations to other formations, as they were seldom needed in the squadrons themselves. In some cases, routine maintenance would be cancelled as there was not enough manpower to engage this task. Yet, it was still important because it paved the way for reconnaissance drones that would soon replace it and surpass its capabilities by a significant margin. Also, to cut Tupolev some slack, they were tasked with building a long-range reconnaissance drone using a system that was designed as a one-way cruise missile. They did the best they could. Many strange proposals were born from the Tu-123. The most absurd of these concepts was a variant employing a nuclear power plant that would fly at Mach 4. Another proposal sought to allow the drone to land in such a way that the entire complex was preserved. This was to be achieved by allowing the drone to conduct an unmanned flight. after which a pilot located inside the fuselage would take control and land the aircraft. Some sources state that at one point both of these concepts were joined into a single variant. Of course, this was rejected because it was, for lack of a better word, delusional. A recoverable variant, designated Tu-139, was developed, using Tu-123 as a base, and was tested throughout the 60s and 70s. The drone promised 10 flights before it had to be decommissioned. I won't go into detail about this prototype, as it did not see service and was cancelled shortly thereafter. In the early 1960s, the Ministry of Defense issued requirements for a tactical reconnaissance drone to supplement the strategic Tu-123. Lavochkin quickly claimed this contract as they proposed an especially cheap and efficient way of getting such an aircraft into service. It was stated that through limited modification of one of their already produced target drones, that being the LA-17, they could satisfy the ministry's demands. This program was designated the Tactical Unmanned Single-Use Reconnaissance Aircraft 1, or TBR-1. The LA-17 target drone began development much earlier in 1950 and was similarly the cheapest option offered to the MOD. Initially, this drone was to operate a ramjet, as this would make it even cheaper to produce. As it was designed to be destroyed, it made sense that it be simplistic to a fault and quickly produced in large numbers. Its fuselage was broken into 3 sections. The front and rear compartments housed guidance equipment, while the center compartment stored fuel. The ramjet, designated RD-900, was located underneath the middle compartment in a nacelle. To provide electrical power to the onboard systems, a 2-blade propeller was installed in the nose. The drone was radio-controlled and featured a tracer, as well as smoke dispensers to display its position in the air. Testing was conducted at the Vladimirovka range in 1951. The drones were launched from a modified Tu-4 that carried 1 LA-17 under each wing. The bomber with 1 or 2 drones affixed to it would climb for 2 hours to an altitude of 8.8 kilometers, and at a speed of 500 kilometers per hour release the drones after the RD-900 had begun to operate in a steep dive. This dive would allow the release to be conducted at speeds of 850 kilometers per hour at an altitude of 1,000 meters. The drone would then begin to function via radio controls. This allowed it to be guided towards the location in which it was to be intercepted. These systems offered 12 to 20 minutes of flight time depending on a multitude of conditions. Pilots operating these drones learned to land them on their bellies at speeds of 5 to 7 meters per second. Of course, the RD-900 was often destroyed in this case, but the fuselage could be repaired and the drone could be returned to service for another flight. State tests took place in July to September of 1954, which determined the following characteristics: maximum flight speed of 910 kilometers per hour, maximum flight altitude of 9,150 meters, and a reliable engine start altitude of 4,300 to 9,300 meters. Even before state tests in 1954, the drone was being prepared for serial production, as competing OKBs could not match Lavochkin's expected price per unit. This was conducted at the Orenburg aircraft plant. The first LA-17 entered service shortly thereafter and was employed until 1956. 6 Tu-4s were modified at plant number 81 in Kazan to carry the targets. The most obvious issues with this system were the inability to conduct ground launches and the engine, which was economically inefficient when compared to a turbofan. To facilitate ground launches, the KS-19 100mm anti-aircraft cannon carriage was modified to support the drone. The RD-900 was replaced with the RD-9E, a variant of the MiG-19's engine. This new system was tested in 1956 and employed engines soon to be decommissioned, designated RD-UBK or short life, as well as the improved MRV-2M radio control system and a new autopilot known as AP-13. Launches were achieved using 2 PRD-98 boosters. In 1958, this upgraded target drone was designated LA-17M and was put into production at the same plant that produced the original model. It was manufactured until 1964. LA-17M featured far longer flight time and offered the ability to install Lundberg lenses to simulate a myriad of aircraft types. This allowed the drone to imitate medium and long-range bombers. Improvements were made in 1962 to increase the altitude at which the drone could operate. This was significant, as LA-17 could now fly between 100 to 18,000 meters. A landing system was also installed to recover drones that were not destroyed through routine usage. This drone entered service in 1964 under the designation LA-17MM. TBR-1 was supposedly created using technology derived from LA-17M, hence why it was called Item 204, LA-17M being Item 203 and LA-17MM being Item 202. According to some sources, the Design Bureau was also instructed to modify standard LA-17s still using the ramjet engine into reconnaissance drones as early as 1956, but this is disputed. Some state that TBR-1 was commissioned in 1957 after this program fell through, but this is not maintained by some secondary sources. Supposedly, these drones would initially operate the AFA-BAF-40R, with the expectation that they would be replaced by the more advanced AFA-BAF-2K later down the line, but this is also not supported. Anyways, in regards to the TBR-1, to turn LA-17M into a reconnaissance platform, the drone was lengthened to accommodate one of three camera types: ASH-AFA-5, AFA-BAF-81, and AFA-BAF-40. ASH-AFA-5 was intended for low-altitude photography with a relatively high degree of detail, around 1 to 1,000 to 1 to 6,000. It was used on reconnaissance aircraft such as the Tu-95MR and MiG-21R. AFA-BAF-40 had a 20-degree field of view and was designed for high-altitude photography. It employed a sliding curtain focal plane shutter with exposure times ranging from 1/150th of a second to 1/600th of a second. The camera was supplied by 120 meters of film and operated in 2-second cycles. The camera is set to operate between 3 to 100 seconds before flight. MiG-15R bis employed this camera. These drones operated the simplified RD-9BKR, which was a non-afterburning variant of the RD-9B. This aircraft featured a pyrotechnic tracer to assist its operator when landing the drone. Some of these drones were equipped with the AP-128 autopilot system, which can be distinguished by a larger vertical stabilizer. TBR-1's autopilot was pneumatic, and the drones employing AP-122 were as a result more efficient, as they optimized air consumption to a greater degree. I should note here that two sources disagree heavily about when TBR-1 entered service. It is stated by Nikolai Yakubovich in his books dedicated to the history of Lavochkin that testing was conducted in late July 1963, which showed that this drone could fly at an altitude of 900 meters and reconnoiter objects 50 to 60 kilometers away from the launch site. If the drone was employing its high-altitude photography configuration, it could fly around 700 meters and capture targets 200 kilometers away. The flight speed was around 680 to 885 kilometers per hour. After these tests, it was claimed that there were 20 produced that year at plant number 495. Yakubovich, among other sources, state that a variant of this drone based on LA-17MM was produced, which employed TV data link, and could be fitted with a radiation reconnaissance package. I've not seen any evidence that these variants exist. Matusevich argues that the TBR-1 entered service in 1968 and was produced at Smolensk. Here they were called LA-17R and were received by units in Latvia, Belarus, and Ukraine. The first of these units was the 83rd Separate Squadron in Kamyanka-Buzka, which was interestingly comprised of former IL-28 pilots. The structure of units equipped with LA-17R was similar to that of formations equipped with Tu-123. The launch platform was towed by a Yaz-214 or 255. Equipment was checked before flight by a diagnostic vehicle built on a ZIL-157 or 131. A specialized vehicle known as KATR-1 was present, which employed a ZIL-164 as its chassis. This system existed to prepare the drone's engines. Cranes, cargo trucks, fuelers, fire trucks, and decontamination vehicles in case of a chemical attack supported the formation. The drone's position throughout its flight was monitored by a radar attached to the formation. Units operating LA-17R were staffed by young officers, a significant percentage of which were lieutenants. This was a result of a program that began in the 70s to integrate more officers into the military, which manifested in the form of technical university graduates being conscripted for 2 years as officers. These individuals made up the bulk of early drone squadrons. Senior officers were not common in these units, with the exception of the formation's commander and his deputies. LA-17R squadrons suffered from identical issues that I mentioned earlier in the Tu-123 section. Since these drones could not be recovered, weekly flights were not possible, and so mass mobilizations were conducted instead, where the entire unit would rapidly assemble and begin a march to a training base 50 kilometers away. Men were roused early in the morning and joined a 60-vehicle column as quickly as they could. Training was conducted when they arrived, after which they slept and returned the next day and put their equipment back in storage. By the late 1970s, the TBR-1 was completely obsolete. It was last launched in 1980, after which all existing models were disposed of. Functional RD-9 engines were salvaged from these drones, and were sent to be converted into high-powered firefighting vehicles. In this case, the equipment on the ground was deemed more unreliable than the aircraft, specifically the A radar, which did not see the production of enough spare parts to keep them functional year-round. Cranes operated by these squadrons were heavily worn, and often difficult to maintain. This was due to the fact that, as a result of their believed inefficacy, drone squadrons were always the first unit to be selected for harvest duty by their superiors. While these early drones were really problematic, when they worked, their performance was exceptional, and the capabilities they offered were, in many regards, unmatched by conventional reconnaissance aircraft. These systems confirmed that with enough development, drones could become a formidable and effective element for battlefield reconnaissance at all levels. And, to the excitement of the ragtag squadrons tasked with operating what was in many regards highly experimental equipment, that aircraft was right around the corner. A characteristic that defined second-generation drones was that they could land, be recovered, and employed immediately after with a relatively short turnover time. This was first conceptualized by Tuполev as early as 1958 with the DP program, eventually designated Tu-130. This was an ambitious proposal, to say the least. Unlike more modern proposals that demanded ground launches as the primary mode of deployment, the Tu-130 would be air-launched. According to studies carried out at the OKB, the aircraft was to be delivered to an altitude of 80 to 100 kilometers. Then, with a 90-degree maneuver, the drone would separate. Interestingly, there was no propulsion system on board. The power supply for the aircraft's subsystems was to be provided from a chemical power source and onboard compressed air supply system. This vehicle was still firmly rooted in the mindset that long-range cruise missiles were the future of intercontinental missile delivery, and this gliding platform supposedly would have offered a cheaper solution when compared to more advanced guidance equipment. Of course, program requirements grew and over-optimism took hold. This system was to be capable of hypersonic speeds around Mach 10, which meant that alongside high-temperature material construction, more advanced navigation systems would be needed. Despite the many complications presented by this tall order, it was decided that several experimental aircraft would be constructed to test the Tu-130's principles. This resulted in a myriad of configurations being tried, which culminated in an entire series of models being built and flown. This allowed the Tu-130's aerodynamic characteristics to be refined. It must be noted that at this time, Tsagi did not have wind tunnels that could simulate hypersonic flight, and so this was easier than trying to construct such facilities. Flight tests were carried out using a Tu-16. This provided Tupolev with information to begin finalizing a rough idea of what the Tu-130 would look like. It was a relatively small system with a length of only 8.8 meters and a wingspan of 2.8. Indeed, the drone looked like nothing produced in the USSR or the world up to this point. The wings featured a leading-edge sweep of 75 degrees and included a great deal of graphite to prevent the system from overheating. The control system included an initial trajectory correction system. After separation from its carrier, the vehicle was to descend at Mach 10 onto the target. The reason I'm discussing the Tu-160 will now become clear. Tupolev proposed something revolutionary that would make this program worth it. While this was believed to be possible with the earlier Tu-100, there was no serious consideration as to how it would be conducted. This revolutionary idea was the ability for the Tu-130 to land, and actually be reused after the fact. This was achieved through maneuvers aimed at deceleration. Air brakes were then deployed, followed by a parachute which allowed the aircraft to drift to the ground and be recovered. Production was actually prepared and nearly finalized for 5 prototype Tu-130s. One was completed and underwent an equipment fitting process. At this time, it was concluded that the best way to launch Tu-130 was an R-12 or R-14. Funding was cut in 1960, and the project was transferred to Pchela. The Tu-130 would eventually inspire many aspects of the Zvezda spaceplane. While this was an unsuccessful program, the prospect of landing an aircraft through the previously described means were pioneered. It is here that I should also clear up the myth that the USSR never seriously considered copying the D-21. It was very quickly realized that this was an antiquated drone that could not be recovered, and worst of all, was impossible to ground launch. Attempts were made, but it was impossible to achieve flight. What Tupolev found most interesting after reverse engineering the D-21 was the application of non-metallic materials, specifically the means in which the fuselage was protected against heat. The black film employed by the aircraft alongside the hollow glass microspheres that made up the fuselage insulation impressed the OKB. There was no way to analyze the reconnaissance equipment as it had been destroyed in the crash, which was assisted by a self-destruction device. It was obvious that a panoramic camera was employed, and they estimated it likely at a focal length between 400 to 600 millimeters. The project was cancelled as the drone was firmly a first-generation UAV. It couldn't conduct photography in adverse weather, it had to be launched from the air, and most importantly, more ambitious hypersonic aircraft were being considered at the time. Tupolev stated that while they could have produced a D-21 analog, there wasn't really any reason to pursue that design, especially considering the viability of single-use strategic reconnaissance drones was disproven in the last decade. Before I begin this section, I should make it very clear that drone development in the USSR up until the conventional reforms in the late 60s and early 70s was hampered primarily by a lack of funding. With much of the budget at this time being directed towards nuclear weapon procurement, the rest of the military suffered. The development of second-generation drones was a perfect storm of recently acquired funding, the maturation of certain technologies, and an idea of what an effective practical UAV required to function on the modern battlefield. On August 30th, 1968, the Council of Ministers of the USSR issued Resolution No. 670-241, which called for the development of a new UAV with greater autonomy, readiness, low-altitude capability, specifically over terrain with varying altitudes, and, most importantly, it had to be reusable. Additional requirements emphasized a diminished RCS, a reduced landing zone, and an engine that was actually reliable. 2 drones were outlined in these requirements, designated VR-2 and VR-3. The VR-2 was intended for Army and front-level reconnaissance, replacing the Tu-123, while the VR-3 was intended for operational and tactical reconnaissance, likely replacing the LA-17R. Deadlines were established. Variants operating photographic reconnaissance equipment were to be demonstrated by 1970. More advanced models equipped with TV equipment and chemical reconnaissance capabilities were extended to 1972. These drones were to be capable of flying at altitudes between 5 to 5,000 meters, and would ideally have a similar service life to conventional reconnaissance aircraft. This was deemed impossible by chief designer G.M. Goffar, who negotiated down to 5 uses. At this time, conventional reconnaissance squadrons across the USSR were being fitted with more advanced supersonic Yak-28R and MiG-21R, alongside MiG-25R, which, while not in service, was being tested. These platforms were impressive and created a great deal of skepticism among Air Force commanders regarding the usefulness of drones. It was ultimately NATO's steady adoption of more advanced surface-to-air missile systems that resulted in this mindset being undone. The smaller VR-3 began its development prior to the larger VR-2, as it was the simpler of the two. The drone would feature a low-mounted, low-aspect ratio triangular wing, with a leading-edge sweep of 58 degrees. In the forward section of the fuselage, small fixed canards were installed to ensure stability while cruising. Elevens running the full span of the trailing edge provided combined roll and pitch stability. VR-3 was primarily constructed from D16 and aluminum alloy, alongside the magnesium alloy AMG6 and composite materials like fiberglass. The drone was divided into 4 compartments, with the first often being stored separately. This section housed all of the reconnaissance equipment. It included a great deal of fiberglass in its construction, which served to reduce the drone's RCS. The second compartment stored the system's power supply and guidance equipment. The third compartment stored the fuel tank, within which ran the air duct channel from the air intake to the engine, along with the fuel pump, fuel accumulator, anti-G device, and hydraulic pump. The fourth compartment housed the TR-3-117 engine, which provided 640 kilograms of thrust, the upper part of which transitioned into the parachute container. Underneath the fuselage, the SPRD-251 solid propellant rocket booster was located. The VR-3 made use of a landing gear made from 3 struts, the forward element of which was stored in the second compartment, while the 2 main legs were placed in the wing consoles. A braking parachute was present to reduce the drone's speed as it approached the ground. A solid propellant motor assisted the braking parachute to bring the aircraft to a stop. VR-3 was equipped with the PA-1 panoramic camera, which was supplied with 120 meters of film. The altitude in which the camera functioned was set automatically, and it often captured 70% of the route. The I-429B TV reconnaissance system available to its alternate configuration could be employed at various ranges. I have yet to find a maximum, but veterans have stated that within 200 meters the image was clearest. Route markers were transmitted throughout the course of the drone's mission, so that the objects it spotted could be located. The drone could also be made to transmit information about the radiation situation on the battlefield along its flight path in real time. There are rumors that a psychological warfare payload was also devised, which carried 19 kilograms of propaganda leaflets carried in 3 containers that would be disseminated over the target, but I've seen no evidence this actually exists, and additionally there'd be no reason to waste a drone on such a mission. The automatic onboard control system, designated ABSU-143, which comprised the DIS-7 Doppler speed and drift angle meter, V-143 computer, and A-032 low-altitude radio altimeter, worked to stabilize the UAV relative to its center of mass, sustain the prescribed flight parameters, issue commands and current telemetry to the reconnaissance equipment, and transmit necessary commands to the landing system. The drone's control surfaces were engaged by 3 servos known as RM-100. VR-3 had a landing area of around 700 by 700 meters, and a maximum takeoff weight of 1,600 kilograms. Unfortunately, the finer details of VR-3's development are unknown to me, as this subject is severely lacking in coverage. What we do know is that after its first successful flight on December 30th, 1970, state trials commenced in 1972, and concluded in 1976, after which the drone was designated TU-143 and entered service shortly thereafter. There are some sources which claim TU-143 made its first flight on December 1st, and others that state this transpired in 73, but more seem to agree with 1970 than those that say otherwise. Even if the exact date is disputed or seldom mentioned, serial production of the complex began while state trials were still underway. In 1973, an experimental batch of 10 TU-143s were constructed at a plant in the city of Kumantau, after which full-scale production commenced. 950 TU-143s would be manufactured until 1989. TU-143 was praised for its high reliability and ability to photograph targets with significantly higher accuracy when compared to conventional reconnaissance aircraft. This was due to its extremely impressive navigation system, which delivered the drone directly over the target with extreme consistency. The TU-143 was also more efficient when it came to the photography of multiple targets in a single flight, as the most efficient trajectory could be planned ahead of time and executed with perfect precision. TU-143 could identify objects with a minimum size of 20 centimeters at altitudes of 500 meters, and below at a speed of 950 kilometers per hour. Even in mountainous terrain, the drone functioned flawlessly and could push altitudes of 2,000 meters. When flying over mountain ranges, the drone would climb to 5,000 meters. Tu-143 featured a maximum range of 60 to 70 kilometers and often flew for as little as 13 minutes. Units equipped with the Tu-143 operated 12 drones each, with 4 being assigned to each squadron, and operated many of the support assets present in the previously described first-generation organizations. They were transported by 4 TZM-143 drone carriers, deployed from 4 SPU-143 mobile launchers, and maintained by KPK-143s, of which 3 were present in each unit. An APA-50M generator set mounted on a ZIL-131 chassis, and 2 KIPS-1, KIPS-2 mobile control and test stations were available to each unit. Photo and video development and radiation analysis transpired within the Pod 3 Information Processing Unit. A UAZ-452T-2 accompanied the unit and recorded their position before launch. The crew sat inside the launch vehicle when the drone was fired. Its roof was made from fiberglass, and its windshield was reinforced with a protective plate that moved into position beforehand. The roof was often momentarily deformed after launch. Pre-flight maintenance was performed on the aircraft, after which it was lifted onto the launch vehicle by a crane. Transport vehicles evacuated the area, and launch vehicles were pre-positioned with the assistance of a 2 T2 theodolite and 1 G17 gyrocompass. The route was then punched into the BVD-1 data input unit. Pre-flight checks were carried out by the SPU-143's crew. After receiving the start command, the boosters were fired and the drone erupted from the launch rail at a 15-degree angle. They were then jettisoned shortly thereafter at a speed of 290 km per hour. This is where the drone entered its cruising period. Values such as the distance traveled from the launch point, the flight altitude, the current geometric flight altitude, and commands to switch reconnaissance equipment on and off were tracked by the control system. After returning from its mission, the landing sequence began, which was quite incredible. Firstly, the drone shut down its engine. Then it performed a rapid climb to burn through its remaining energy. Once the drone's speed had been sufficiently drained, it automatically deployed its braking parachute. After 11 seconds, this parachute was jettisoned, and the landing parachute was deployed. This allowed the drone to descend vertically. Before impacting the ground, the landing system instructed the drone to orient itself into a horizontal position, as its landing gear was deployed. Special probes sensed when the drone had nearly made impact with the ground, which gave the signal to fire the braking rocket, reducing its speed from 6 meters per second to 2. Upon the compression of the landing gear, the motor and parachute were jettisoned. Following its recovery, the Tu-143 could be made ready for flight within 4 hours. To develop the SPU-143, Tupolev visited ZIL on July 6, 1966, and together with the head of the Air Force Directorate, V.M. Romanenko, the ZIL-135P and fueling vehicles were inspected. This left a lasting impression on Tupolev, as he was already personally acquainted with those working at ZIL, which is partly why the BAZ-135MB was chosen as the basis for the SPU-143 and TZM-143. The ZIL-135 was originally developed to deploy cruise missiles and was chosen as the launcher for the land-based variant of the P-5. It was also the vehicle tasked with firing the P-35B. As the system was produced at Briansk, it was redesignated to BAZ-135. Much of the technology that allowed the SPU-143 to be capable of withstanding the Tu-143 was pioneered years in advance, which made things especially convenient for Tupolev. These units were deployed twice a year for large-scale exercises. During these endeavors, the drones were shadowed by fighter aircraft which would shoot them down in case they lost control. While these units did have relatively low flight hours, all they really had to understand was data processing and rapidly getting the drone into the air. Everything else at that point was then handled by the aircraft. Supposedly one of these drones was lost in 1986 in East Germany. It was equipped with the TV reconnaissance pod. You should go and try to find it if you live in Germany, and then send me the reconnaissance pod. This is not a joke. I don't believe this drone was ever located, so, you know. It is unknown how often these units drilled. It is unlikely that more than a handful of flight hours were accumulated per squadron each year. Some sources claim that Tu-143 was present at Zapata 1. It's unknown if it was actually there, particularly in the exercises, but it's stated by some that 3 launches occurred. The 1982 publication Zapata 1 does not mention Tu-143, so it is possible that the author was mistaken and none of these aircraft were present. 24 squadrons would be equipped with this drone before the collapse of the USSR. Following the Chernobyl disaster, the application of Tu-143s was proposed. as they possessed the ability to safely conduct radiation reconnaissance without endangering pilots. At this time, the chemical troops were already flying at varying altitudes along the radioactive plume. Because of these tactics, the trajectory and range of the disaster's effects could be estimated with precision and safety from aircraft like AN-24RR. While it is true that Tu-143s could have been useful in the ongoing hunt for ejected fuel rods that were being located with black and white aerial photography, this was an action far too methodical for Tu-143. Helicopters were already tracking combustion products and large-scale ground reconnaissance was underway. This required a significant amount of equipment to be decontaminated, measured in tens of thousands of tons. The proposal was finally rejected, and while the reasoning for this is unknown as of writing, it's not difficult to imagine that the complexity of the task was simply too much. Furthermore, I can imagine that fears of an ionized drone losing control and crashing outside the disaster area were brought up. Hunting for a radioactive drone that then had to be deconned was probably just too much effort. An attempted modernization of the Tu-143 was the Tu-243. No one can agree on when this system entered service. Some sources claim that it was accepted in 82, but I'm going to stick with the more accurate and frequently repeated number, which is 87. The reason that this number is more believable is because the drone had not yet been conceptualized until March 6 of 81, when the USSR Council of Ministers issued Resolution number 249-76, which called for the development of the VRZD, which would eventually become the Tu-243. The drone's requirements were approved in February of 1983. The Tu-243's first test flight took place in July of 1987. It entered production shortly thereafter at the Kurmutau machine building plant. It was stated that this drone offered a 2.5 times increase in effectiveness compared to Tu-143. Initially, the drone was equipped with the PA-402 panoramic camera and the AST-M television reconnaissance system, which transmitted in real time over a TRASA-M radio link, which is viewed through a 30-second delay after overflight. Depending on the importance of the information, this delay can be modified. Usually objects of importance appear around 10 minutes after launch. The second variant integrated the ZIMA-M thermal imaging system. This increased the total area it could reconnoiter per mission to 2,100 square kilometers. Tu-243 was additionally equipped with a new guidance system, called NPK-243, which made the drone significantly more effective. A new, lighter, and more powerful booster was affixed to facilitate launching the drone with its increased takeoff weight. It was designated RDDT-243DT and had a maximum thrust of 14,820 kgf. The drone came with a new set of support equipment, including the SPU-243, also known as SPU-143-4, built on the BAZ-135MB. Reloading it was performed by a crane mounted on the TZM-243 transport vehicle. KPK-243 and Pod 3D replaced their respective models in the squadron organization. Supposedly, the Tu-243's range was expanded to 360 kilometers, but that's kind of optimistic. The larger VR-2 would be developed using much of the technology employed to construct the Tu-143. Its technical requirements were as follows. The aircraft had to be capable of achieving a depth of 500 kilometers, even in complex meteorological conditions, and at night. It had to be capable of transonic dashes at speeds of 1,300 kilometers per hour when evading air defense, and cruise at a speed of 1,100 kilometers per hour. 5 unique payloads were envisioned to allow for all-weather day and night capabilities. Additionally, new cameras had to be developed to meet requirements, which necessitated a resolution no worse than 15 centimeters for daylight photography, and 30 to 40 centimeters for infrared reconnaissance equipment. The problem was that despite the long history of drone development that predated these systems, nowhere in the world did equipment exist to realize these demands. As a result, requirements were relaxed somewhat. Issues arose almost immediately when concerning the modular payload concept, as each set of reconnaissance equipment differed in size, meaning that interchangeability was impossible. Unique variants had to be employed instead. This actually turned out to be somewhat cheaper than original estimates. The first variant was designated Set 1 and included two A86P cameras, which from an altitude of 100 to 1,000 meters, photographed an area of 6 multiplied by the height times 160 multiplied by the height meters, with height obviously corresponding to the aircraft's altitude, which was usually around 300 meters. Assuming the drone was flying at the previously described altitude, it would be capable of detecting a target measuring a minimum of 30 centimeters. Set 1 also came equipped with a panoramic camera designated PA4-90, which could photograph an area of 10 times the height of the aircraft by 450 times the height of the aircraft with a resolution of 40 centimeters. Set 2 was intended for reconnaissance at night. This was an especially difficult task, especially for a drone, as all conventional reconnaissance equipment required light to function. To solve this problem, this variant was equipped with a thermal imaging system designated ZIMA. It was designed at the All-Union Lenin Energy Institute. ZIMA's chief designer was I.A. Labanyev. This allowed Set 2 to capture a zone of 3.4 multiplied by the aircraft's height by 230 multiplied by the aircraft's height, which at an altitude of 1,000 meters supposedly worked out to 3.4 by 230 kilometers. Though it was noticeably less precise than Set 1, with a resolution of 70 centimeters. The device required targets to exhibit an 0.3 degrees Celsius difference when compared to the background. It is stated that signal intelligence and radiation reconnaissance sets existed along these primary models. It is claimed that the drone's application of an S-duct, like the Tu-143 in composite construction, reduced its RCS enough that surface-to-air missiles could not reliably engage it. One of the requirements was to thwart air-to-air missiles like the AIM-7. It is unknown if this was actually successful. The variant of AIM-7 is not specified. VR-2 was deployed similarly to Tu-143, but instead of a dedicated launch vehicle, the drone was fired from a towed launch platform. This meant that the drone's boosters had to be adjusted before flight depending on the terrain. Almost all of these supporting assets are identical to those present in Tu-143 squadrons, with the exception that they are meant to serve as VR-2. VR-2 was designed with increased secrecy when compared to its smaller counterpart. A team of specialists was assembled at Tuполева who were especially qualified, such as A.A. Frolov, who headed the fuel design team, U.M. Kushnikov, who managed all pyrotechnic equipment, N.I. Solotenkov, who worked on hydraulics, and G.N. Orlov, who was tasked with creating the parachute. S.A. Vigdorchik, head of Tupolev's technology department, emphasized that when possible, existing subsystems should be employed to reduce development costs. This was an effective approach that shortened R&D by a significant margin. While the VR-2 was in development, the design team was faced with a common yet deeply infuriating complication, a radical change in requirements. It was stated that now the drone had to be a simple, inexpensive operational reconnaissance platform, and that after calculations had been conducted, the speed of 1,300 kilometers per hour was no longer required to thwart enemy air defense. It was decided that 900 to 1,100 kilometers per hour was acceptable. This turned out to be a net positive as the drone got significantly lighter and less complicated, as the afterburning engine alongside the variable intake could be removed. The fuel load was also reduced. This also diminished the probability of infrared missiles being able to destroy the system. The R9A300 was chosen to satisfy these new requirements, which was a converted non-afterburning variant of the MiG-19's RD-9. The primary advantage that this engine offered the VR-2 was that they were already available in surplus, and therefore no new engines would need to be manufactured once the drone entered production. The most expensive piece of equipment on board the VR-2 was also made less expensive. This was the ABS-U-141 control system, which now did not need to manage supersonic flight. Subsonic flight was significantly easier, and had already been tested on the Tu-143. This did not mean the ABS-U-141 was a simple system. It had to manage 3 turns and 6 altitude changes along the drone's flight trajectory. Originally, the VR-2 was to land without relying on a parachute, but it was eventually decided it would be much simpler if the Tu-143's landing regime was replicated. This was the better choice, as a large unprepared area to land VR-2 would be hard to come across in real combat conditions. Due to the size of the VR-2, it had to employ a unique parachute with an area of 950 meters squared. This made it the largest parachute produced in the USSR, surpassing those employed by the Soyuz descent module. While the aircraft performed its landing, it jettisoned its ammonia coolant designed to keep all sensitive equipment on board stable throughout its flight, which made the drone appear as if it was smoking, but this was in fact standard procedure. There was only one recorded case of VR2's landing system failing while it was being tested, which manifested in the drone burying itself nose first in the ground. After the drone received the designation Tu-141, a small batch intended for testing was prepared at the OPIT plant in Moscow. The first of these experimental models was ready by early 1974, and by December, flight tests were already being prepared, which resulted in a successful launch. In 1975, serial production was approved. The HAZ plant in Kharkiv was chosen to manufacture the system. Personnel from Kharkiv, including one of the plant's directors, traveled to Kuomintau where the Tu-143 was being prepared, to familiarize themselves with the production process. This was due to the fact that the tooling to manufacture the two drones were very similar. They actively participated in manufacturing Tu-143s. In November, specialists from HAZ arrived in Moscow to receive Tu-141 airframe schematics. The following year, in January, a similar trip was conducted to collect documentation on the drone's electronics. At this time, HAZ was occupied producing the KH-55 and Tu-134. Adding another unique system to the factory's team would prove difficult, and so a subdivision was created, designated Sector No. 5, who would handle the Tu-141. In 1982, this organization would be transformed into its own department and redesignated No. 136. As the plant had not yet worked with composite materials present on the Tu-141's airframe, a brief period was spent learning how to handle them. It was necessary to re-equip the factory with unique tools to process these materials. The first batch of serial Tu-141s was produced in 1977. Issues immediately arose relating to the introduction of coolant into the airframe, as there was no nearby facilities to work with ammonia. An organization known as Silkozhchemia was contacted, who supplied the material and handled its processing. As the drone was a highly secretive project, the tanks present within the aircraft were usually filled at the end of the workday. This was unfortunately a bad decision, as exhausted personnel who wanted to go home filled these tanks to the brim. This resulted in rapid expansion under the sun, causing them to rupture. This was a somewhat problematic incident, but not a major chemical disaster. Future fillings were conducted with greater precision. HAZ created its own ammonia department so that greater supervision and professionalism could be exhibited during the process. Documentation was also revised for more clarity. Instead of 24 plus or minus 1 liter, it now read as 24 minus 1 liter. This was meant to convey that the tank could be underfilled by up to 1 liter, but not the reverse. When testing Tu-141s to determine the efficacy of the landing system, the drone swung about, sometimes rather violently, beneath the parachute. This resulted in the aircraft frequently impacting the ground with the forward landing gear before the rear, putting all of its weight on the single strut. This caused breakages, which didn't destroy the drone, but nevertheless it had to be resolved. First, the landing gear was strengthened, but this also failed, and individuals testing the device complained that they had to replace it with every flight. After further attempts to resolve the problem, which often only made things worse, by tearing entire chunks from the aircraft upon landing, it was determined that the forward landing gear breaking was actually what allowed the drone to land safely. For a moment, it looked like this was going to become a feature present on the final model. Of course, this was deemed absurd and the problem had to be solved. Because reinforcements failed, the parachute deployment parameters were adjusted and the aircraft's control surfaces optimized. The braking rocket's angle was also adjusted alongside the length of its probes. This was done by changing these values by microscopic increments with each successive test flight, until the drone landed without issue. Tests were often conducted in Moscow at the Gromov Flight Research Institute. It was eventually deemed too dangerous to fly experimental drones with such a wide flight radius in the vicinity of civilians, and so subsequent trials were moved to the Karakum Desert, which you should remember from my Pipeline Troop series video. Other testing locations including Lake Balkhash, the Vladimirovka Range, and the mountains of Kazakhstan. Representatives from the Ministry of Defense, the Air Force Procurement Directorate, and personnel from conventional reconnaissance squadrons were invited to these demonstrations. Many of these individuals stated they enjoyed the desert even if the conditions were extreme. It is unlikely they would have said this if they were assembling hundreds of kilometers of PMT-100s. The temperatures on both ends of the spectrum proved the most difficult aspect of testing, though. It was jokingly stated by those in attendance that if the drone could handle these grueling conditions, it would never let you down in Europe. For the test flights, areas were chosen that were especially far from civilization. What the design team forgot to note was that nomadic populations still living in the steppes were present in the area. This was realized when one of the drones deviated from its flight route and landed directly next to one of these camps, where a wedding was in progress. The appearance of this large, unidentified object landing, supported by a rocket motor, made village elders believe that it was a sign from heaven. Luckily, there was no altercation between the individuals. For unknown reasons, during these tests, locals, if they found the parachute, would steal it. For this reason, the recovery team had to act fast and ensure they reached the parachute as soon as possible. It was jokingly stated that this was a way to test the recovery speed under realistic combat conditions. Because Mi-6 and Mi-26 were not available to the team, they tried to requisition Ka-27s, but this was not possible, and Mi-8s simply didn't possess the lift capacity to carry the drone. For this reason, automobiles had to be employed, which made racing to the recovery site rather difficult. As Tu-141s were transferred to formations for testing, problems occurred due to a lack of experience operating the system. In one case, the barometric altimeter was set incorrectly, resulting in the control system believing the drone's position was hundreds of meters off from where it was actually located. This ended in a collision with the terrain. Funnily enough, despite the crash, the landing gear deployed properly and all the fuel and ammonia was jettisoned, after which it caught fire and had to be written off. Another drone had its parachute improperly stored throughout much of the winter. This resulted in it having to be repacked and dried off. It was wiped down with alcohol and eventually looked usable again, but this was quickly disproven when the canopy collapsed upon descent, causing the drone to plummet to the earth. In 1979, the first Tu-141s were delivered to their squadrons. The first production batch was entirely Set 1 and featured a new engine, the KR-17A, created by the UFA Production Association. It was a relatively inexpensive engine intended for cruise missiles. The Tu-141 was never exported, as it was more advanced than the Tu-143 and therefore contained sensitive components like its thermal imager. For a time, all of the Tu-141s in service were fitted with the first equipment set. Eventually, Tu-141s were modified to feature an RPM control system that allowed engine speed to be shifted while the aircraft was in flight. Series 18 Tu-141s were finally fitted with the Zima thermal imager. Already produced aircraft began to be rebuilt to incorporate the optic. Alongside signal intelligence variants, it was stated that these drones possess similar capabilities to modern reconnaissance aircraft like the Su-24MR. Pilots trained to intercept the Tu-141 and found this rather difficult. The aircraft had to make several turns to engage the drone as they would frequently lose sight of it. One pilot said that he was startled when looking for the drone as he turned and saw that it was flying directly next to him. While the Tu-141 and Tu-143 were successful in providing higher-level reconnaissance, a system like the LA-17R was still missing. Something capable of flying near friendly formations and obtaining information about individual targets on the battlefield. This resulted in the STROI program, which began in 1982 at the Moscow Ministry of Radio Electronics Industry. Several systems were proposed under this program. The regimental STROI P, named Pchela, the STROI A, which would be employed at the army level, named Dyatlov, and a semi-strategic reconnaissance system to complement the Tu-141, known as STROI F or Korshin. Alongside the Korshin, the Orel was proposed. The STROI program also led to proposals for a UAV capable of carrying precision weapons. This never went anywhere. There are some sources which state that the Pchela was intended for use with the VDV, but this is disputed or only partially agreed with. It definitely wasn't only for use within the VDV, that's for certain. The drone was to be cheap and as simple as possible. This was done to make up for the fact that it would be spotting targets of lower priority than those of Tu-143. The drone was of course to be reusable and capable of many flights before it had to be decommissioned. Deadlines were set for February of 1983. The most expensive component employed within this complex was to be its TV reconnaissance equipment. Nothing could exceed the price of this system. The fuselage was broken into 3 sections, the first of which housed the reconnaissance equipment while the center compartment contained the fuel tank. The drone employed a 2-cylinder 20-horsepower engine with a displacement of 274 cc, designated P020, developed at the Kubyshev engine plant. This engine drove an AV-23 two-bladed propeller. Pchela was equipped with a parachute recovery system installed atop the center compartment. The aircraft was cushioned by an inflatable bumper deployed before impact. On the 21st of October 1982, a mock-up was prepared and launched to confirm that the system could be made airborne. On the 3rd of November, the drone was launched from an early prototype of its accompanying launch vehicle. Engines were delivered on the 24th of January 1983. They were fitted to prototype drones that same day. Additional components were being trialed on the ground in Moscow simultaneously. On the 5th of March 1983, during an especially cold morning, launches were prepared. The drone was fitted to its deployment platform, only for the team to realize the boosters required to fire the system were indoors being warmed up for the test. After a 40-kilometer mission to retrieve them, the test began an hour late, much to the chagrin of those forced to monitor the drone in the freezing temperatures while this transpired. After a great deal of anticipation, the tests began, and the drone's control system failed, causing it to crash. The issue was believed to be with the launch mechanism, and so a catapult was chosen over the methods employed by all previous UAVs. This did not satisfy, and so a catapult assisted by a booster was chosen as a reasonable compromise. On the 17th of June 1983, the drone made its first successful test flight. A recovery net was employed to capture the drone, very similar in its design to the system used to recover MQM-105. After some celebration, the team got back to work preparing for the second launch, which was to be conducted on the 28th. This test was successful, although the UAV for a short period failed and began buzzing the team at low altitude before continuing on its pre-programmed flight route. The flight lasted 15 minutes before the UAV landed. After additional testing throughout 1983, 15 launches were conducted, 10 of which were successful, which looked promising to Yakolev. On the 28th of May 1984, a final flight was conducted as part of joint trials, after which 23 prototypes were manufactured for further testing. By this point, 25 launches had occurred. On September 25, 1985, the OKB was ordered to manufacture a pilot batch of 50 Pchelas. This was successfully engaged at No. 475. The drone was refined from May to December of 1987, and in April of 1988, the drone was finally delivered to the troops. Mirroring proposals for a countermeasure dispensing drone to protect naval cruise missile launches developed in 1970, there was supposedly a variant of Pchela designed to jam enemy communications on overflight, but it's unknown if this was actually considered. Many experimental variants were devised as its development was pursued, such as the DPLA-61, which featured a proper landing gear, redesigned wings, a unique recovery parachute design, and a new power plant. This model was trialed on the ground in December of '84. The UAV made its first flight on the 26th of April, 1986. After a spectacular avionics failure, the drone was refined and recommended for service, under the designation Styrk. During the UAV's acceptance trial, 68 launches were conducted across 13 examples. 52 of these flights were successful. Finally, the system was tested in mountainous terrain in September of 1989. Here, 13 UAVs accumulated 50 flight hours. Unfortunately, 6 prototypes were lost during these trials, demonstrating a 46% failure rate. Still, the drone was recommended for further consideration. And then, the USSR collapsed.